So today I'll be talking about comparative parametric study on physical and chemical accelerators. It's just a part of the study, but I'll try to give as many parameters as we could, figure out what influence the accelerators in a cementitious system. But the first question is, why do we need to study accelerators? They're already being studied for a long time now. Calcium chloride has been studied since 1950s or 1960s, but why do we need to study them? The issue is once you look at the literature, what happens is uh, all the literature, it has different water cement ratios. Your clinker chemistries are different, especially the sulfate content in the system. Your temperatures at which they have been tested or relative humidities, they'll be different, and the fineness of cements is also different. And cements also have evolved since then. Other part is why the physical accelerators. There's very limited data. There has been some data since 2009 on physical accelerators, how they work, how they behave, but what's their influence, how do they work in mortars as compared to paste. That has not been fully studied yet. Then we have changing needs of our mixed designs. For durability purposes, we need low water cement ratios. We are adding more admixtures. So the compatibility between those admixtures, the effect of low water cement ratios, what does have an effect on working mechanism of these admixtures or efficacy of these accelerators. Then the third one is your plastic yield stress and demand for plastic yield stress in digital concrete. For 3D printing, one more parameter which has been added instead of our setting time is your critical yield stress. That means the critical yield stress is nothing but it's the yield stress after which you can start putting one more layer on top of your initial layer. So the rate of gain of that yield stress will determine how fast we can print a 3D printed system. So typically what we are doing in 3D printing now is we are using accelerators which mainly target the illuminate phase of cement. So we put it at a nozzle like a shotcrete, do secondary mixing, and that increases the plastic yield stress. But what happens to this these admixtures once you change the temperature and other parameters, that has not been fully studied yet. So that was what was the motivation for this study. So for this study, based on ACI 212, we took 6 accelerators. We took a calcium chloride-based accelerator. We took 2 non-chloride accelerators. One is your sodium nitrate and sodium thiocyanate combination, and then second one is your calcium nitrate and sodium thiocyanate combination. And then we took 2 nucleation-based admixtures. One is the admixture with CSH and TIPA, that is XS55. Then you have admixture with CSH and sodium thiocyanate, and it also has some traces of salicylic acid and calcium salts in it. And then we have a last accelerator is our aluminum sulfate based accelerator. So we have named all of them. So typically sodium nitrate is more an antifreeze admixture, but it also does have an effect on the hydration reaction, which we'll see in this presentation. So we did limited rheology testing. We did hydration kinetic testing with isothermal calorimetry. We studied how physically the microstructure changes with the ultrasonic pulse velocity testing, and then we did some phase evolution with thermogravimetric analysis and some mechanical properties in terms of shrinkage and compressive strength. For all these studies, we changed our water cement ratios, we changed our dosages of admixtures and aggregate cement ratios, cement type. So we were changing one parameter and looking at all the effects of that parameter on the behavior of these accelerators. So first what we did is we noticed that once we add these nucleation based accelerators, especially they get easier to mix. So when we looked at the yield stress of those materials, for example XS55 here, they reduce significantly as compared to control at a 0.39 water cement ratio. Similarly at 0.42, you also have a reduction in the plastic yield stress of these materials. So they are affecting the rheology when we are adding them in. All the admixtures do change rheology below zero point 0.4 water cement ratio, but at 0.42 there's not much difference except in case of these nucleation based admixtures. The aluminum sulfate based admixture precipitates ettringite so fast that you cannot test it in a normal rheometer. So what we did is we took an EN445 flow cone. So in EN445 flow cone, what is done is you take a particular volume of cementitious paste and check how much time it takes for it to flow through the orifice for a particular volume. So in this case, it was 200. So when these two black two lines are your control, which is type 1, which is the square here, and type 3 is the triangle here. So when we added sodium aluminum sulfate based accelerators here, they significantly increase the demand of your high range water reducer, as well as they increase the time it takes for the cement to flow. So they significantly increase the saturation dosage. Saturation dosage is the dosage after which your high range water reducer cannot change the workability of your system. So they are extremely potent in reducing your workability. That's why they cannot be added with the cementitious system in 3D printing or any digital fabrication. They have to be added as a secondary admixture. So then we wanted to see what happens to the workability or flow of these admixtures when you add them in secondary mixing. So we took a particular dosage of aluminum sulfate based admixture at 0 minutes, 3 minutes, 5 minutes, and 10 minutes. What we saw is that there is significant loss of workability even if we keep the dosage same and we add them in as secondary admixtures in secondary mixing. Then we'll be talking quite a bit about isothermal calorimetry. So typically our cement has 4 main phases and gypsum with them. So C3A, C4AF, halide. So what happens is when you add water to cementitious system, you get heat of dissolution. That means that earlier C3A reacts with water and you start forming ettringite, but then your sulfate comes in, it retards the reaction. You get your main silicate phase, then secondary sulfate depletion phase. So we did a study on what happens to the cementitious paste when at 23 degrees and a particular water cement ratio, which is 0.42 in this case, and see how much the accelerators accelerate the cementitious reaction. So a disclaimer, in this case, we have taken the time of data collection from 3 to 4 minutes. We have not taken out the first 30 minutes. There's a reason for that. So I'll be discussing that in a while. So with calcium chloride based admixtures, as seen in literature, they reduce the setting time significantly, or the main silicate peak onset significantly, and they increase the main height of the main silicate phase. So, but what happens is after a certain dosage, you stop seeing this secondary sulfate peak. That is because there are a lot of Friedel salts being formed in the presence of chlorides and other chloroaluminate phases which are being formed in chloride-based admixtures. Then with sodium nitrate-based admixtures, we saw that there's no effect on the setting time or the onset of your silicate reaction, but your height of the silicate peak and after a certain dosage, height of your aluminate peak is significantly increasing. That means it's messing up with the sulfate content in the system. With calcium nitrate-based admixtures, they behave as we have known them to behave. They accelerate the reaction of silicates and then also increase the height of the silicate peaks, which translates into earlier strength development. So with our chloride-based admixtures from low to high dosages, we found that heat of hydration increased by 14%. For sodium nitrate-based admixtures, it increased by 10 to 14%, and for calcium nitrate-based admixtures, it increased by 3 to 6%. Then we looked at the nucleation-based admixture. So what was interesting to see in first nucleation-based admixture was, which is XS55 here, there's a significant retardation in the onset of main silicate peak here. It is pretty significant because it's in hours, not in few minutes. So we were wondering why is this happening. So we don't know the full chemistry of this admixture, but it's a combination admixture which has CSH seeds which act as nucleation agents, but then you also have TIPA in it, which precipitates ettringite very fast in early ages. And one more theory what we have is because this affects the rheology of your system, there's a polymer-based dispersing agent to distribute these seeds properly in the cementitious system. However, after that initial retardation, it behaves the best among all the accelerators, and we get a 7-day heat of hydration increase of 22% as compared to control. Then our second set of nucleation-based admixtures, what they do is they increase the setting time as well as the main hydration, main silicate peak height, and that means they are accelerating as well as hardening accelerators. And then the 7-day heat is increased by 9 to 11% in them. Then comes the aluminate-based admixture. So they were they were the main reason why we didn't take out the initial time in the isothermal calorimetry data. So you see here they do accelerate this silicate peak, but there's no reaction which happens between aluminates and silicates. How they increase the acceleration in early ages is they have a very stable reaction with C3S to form attringite for first 30 minutes, so that they gain yield stress very rapidly. And then this acceleration here between control and the illuminates, this is because when this 30-minute attringite is formed, the heat becomes so high in the system that it's accelerating the reaction. So this is not, here this does not mean that aluminate sulfates are reacting with silicates, but it's just that the heat of the system is higher. So then it also gave a 15 to 20% increase. Even if we exclude this peak, still we have about 5 to 10% increase at 7 days in heat of hydration. Then we wanted to see what happens to these admixtures if we change the water to cement ratio. So we took two water to cement ratios, 0.42, which we discussed just now, at 2 dosages, not 4 dosages, they are low and high dosage. So what we saw is at low dosages, except for SU, which is the aluminum sulfate admixture, you get slight retardation. You don't get much retardation in any accelerator except for XS55, which we saw earlier. But when you go to 0.36 at low dosages, all the admixtures retard. Here, there's no aluminum sulfate because it could not be mixed in the same with the same conditions as we were mixing the other accelerators. So we haven't included that data. So also at 0.42 water cement ratio, we have a very good delta between control and different admixtures. But once we go to 0.36, the efficacy of these admixtures at 7 days starts to reduce significantly, and only Exceed shows some increase, significant increase in terms of as compared to control at 7 days. Then looking at 0.36 water cement ratio and 0.42 water cement ratio at higher dosages, so we see that okay, we know that aluminate is increasing the aluminate sulfate is increasing the aluminate reaction, but here if you see high dosages, the aluminum sulfate and chlorides are similar in terms of when the onset of silicate peak is there. Excuse me. Similarly, you see the only thing which changes between high dosages is that the magnitude of this retardation or acceleration changes. But again, at high dosage also we see that there's a very good delta between control and admixtures at 7 days in terms of heat of hydration, but the heat of hydration significantly reduces here for all admixtures except XS55. Then we wanted to look at what happens with temperature. If we change the temperature of these admixtures, accelerators, what happens? So the dotted lines here are 23 degrees, that is just for comparison, and solid lines are the 10 degrees. So one interesting thing what we saw is the sodium nitrate based admixture, it did not accelerate the silicate peak at early ages, but at later, at 23 degrees, but at 10 degrees, the main silicate peak got significantly accelerated here. So they started behaving as an accelerating admixture in addition to a hardening accelerator. So that was one of the significant differences here. In addition to that, we saw that the peak of our aluminum sulfate based admixtures is significantly retarded at 10 degrees, so they don't behave as good as they behave at 23 degrees. So talking about the heat of hydration at 7 days, for chloride based admixtures it was about 0 to -3% as compared to control. And then for sodium nitrate based admixtures, it was minus 0.5 to -3%. And then for calcium nitrate based admixtures and the XS55 and XS44, it gave a positive value. And for the aluminum sulfate based admixtures, accelerators, it reduced by up to 5% with different dosages. So then we wanted to see what happens if we have limestone in the system and the fineness of the cement is different. So we took type 3 cement and type 1 cement at different dosages. This is low and this is high. What we saw is the retardation here is the retardation of the XS55 was not seen in as significantly in type 1 cement as compared to type 3 cement here. It's not visible. Oh, I'm running out. Okay. So I'll skip this slide, but there was significant difference in terms of how the admixture accelerators behaved in 23 degrees and 10 degrees and with water cement ratio and binder composition and the fineness when they were changed. And then we looked at ultrasonic pulse velocities of these cementitious systems. We used a particular mixing method where we can get a very particular liquid to solid transition in ultrasonic pulse velocities, and all the values from hydration kinetics to isothermal calorimeter had a very good correlation with the ultrasonic pulse velocity. So we think that this is the best method to correlate the hydration kinetics to your physical transformation in the system from liquid to solid phase. We also looked at the activation energies. This is the last part I'll discuss today. At 0.42, activation energies of all these admixtures for initial setting time and final setting time were significantly less than control. But when we went to a lower water cement ratio, the activation energy is significantly increased, except for NCL, where they behave as setting accelerators at 10 degrees centigrade as compared to 23 degrees centigrade. So we did some shrinkage tests, but we don't have the time to discuss these. If you want to learn more about this, we can discuss after the slides. Then the conclusions were the accelerators behaved very differently once you change the water cement ratio, temperature, limestone content. UPV correlated very well with heat of hydration. Isothermal calorimetry data does not compare very well with the setting time, bicatenary setting time data. And aluminum sulfate based admixtures cannot be tested with our conventional testing methods, and we have to develop new testing methods for them. And the future study is that what we saw is once you add limestone to the cement, the sodium nitrate based admixtures start adding air into the system. That has to be further investigated, why there is air in the system. Through UPV, we can understand what's the air content, initial air content of the system, so we can understand that. So then we are also looking at interaction between high range water reducers, VMAs, and aluminum sulfate based admixtures, and doing some in situ XRD. Thank you.